Okay, here we go. All right, what ones do you have questions on?
28.
Okay. These up. All right, let's check out 28. All right, this is the frictional forces section. So in 28, it says a box of bananas weighing 40 newtons rests on a horizontal surface. There's a free body diagram. The coefficient of static friction between the box and the surface is 0.4, and the kinetic coefficient is 0.2. No horizontal forces are applied for part A to the box, and the box is at rest. How large is the frictional force exerted on it? So for part A, it has to be 0. Because if nothing, remember, if something's not sliding or trying to slide, there's no friction. Okay? So if those were the only two forces on it, like it says to begin, then none of those mu values even apply. There's no friction as long as it's on a flat surface. Does that make sense? Okay. But remember, we gave examples like if I put the tiniest little force on an object, that proves now there's friction. Otherwise, it would do what? Move. And that's like when we took away the friction with the little hovercraft here. Little tiny force does make it move, right? But it only, especially static friction, it only pushes with what it has to, and it doesn't have to push back with anything if nothing's trying to move it, right? All right, so moving along to part B then. It says, what is the magnitude of the frictional force if a monkey, I don't know why a monkey, I guess because of bananas, if a monkey applies a horizontal force of 60 newtons to the box, and the box is initially at rest. All right, so we could use these values now to figure out some frictional forces and see what's going to happen. So it tells us the monkey is going to put a horizontal force of 6 newtons on this thing. All right, so let's go to the static friction first, because it starts off not moving, right? It said initially at rest. So don't forget that this isn't actually an inequality, right? So if we plug in the numbers, the static friction is less than or equal to 16 newtons. Frictional, kinetic I figured out for another reason, for not this part. So this is what matters here. And here we just got to understand what that means. Remember, you could keep pushing and pushing and pushing on this thing, and it won't move till you just get past how much? Breaking point, which is 16 newtons, right? So this isn't the answer, but that helps me. The rest of it's really just a concept to answer this. And so I put a little note here, what I'm just talking about now. It will not begin to move until 16 newtons is applied. So therefore, if a monkey only applies 6 newtons to it and it was at rest to begin with, then it'll push back with how much? 6 newtons to balance it out, right? It can't push back with more. And the monkey's not pushing enough to reach that max, right? So that's how we figure out that part. That makes sense? Okay, so we move on. It says, what minimum horizontal force must the monkey now apply to just start it in motion? So to just start it in motion, now we reach that breaking point, right? And we already actually figured that out up here, all right? Once we press at 16 newtons, that's when it's going to just start to move, okay? So we didn't have to figure anything out there. It's just using that same concept, right? And then in part D, what minimum horizontal force must the monkey apply to keep the box moving at constant velocity once it has started? All right, so it's the monkey got into motion, right? He's in motion, now he's pushing this thing at constant V, all right? At constant V, forces have to be balanced, right? But we're in what kind of friction now? Kinetic, since you're sliding. So all right, here I found what the kinetic friction, and this is always an equality. There's no breaking point anymore because it's already in motion, right? So this tells me, using the mu from above and the normal force from above, that we get a kinetic of 8 newtons once it's sliding. So the only way to balance that out is to push it 8 newtons, right? So once it's already moving, if this monkey continues to apply the force in the opposite direction to balance it, it will continue to move at that. Does that make sense? Okay, so most of this stuff was like using these two formulas, just making sure you interpret the situations right based on simply finding the max static and then what the kinetic is. And then finally, part E, if the monkey applies a horizontal force of 18 newtons, what is the magnitude of the frictional force, and what is the box acceleration? All right, so the frictional force, this is always an equality, right? It's still sliding, even when I push hard enough to accelerate it, right? So that doesn't change the fact that this isn't 8 newtons, it still is, okay? So now we got to set up Newton's second law, though. Sum of all forces on the x-axis, right? I have an applied force one way, we'll call the positive direction, and we'll subtract off kinetic friction, right? Equals ma, we know m, we know kinetic friction's 8 newtons, and we know the applied force is 18, so we just got to solve for a by dividing over the mass, which is 4.1. And if you're pushing with 18, you have clear unbalanced forces, so you're going to speed up if you're pushing harder than what friction's pulling, right? And we speed up with an acceleration rate of 2.43 meters per second squared. So mainly that problem was all about like how much we understand static and kinetic friction and how they all work. Does that make sense? All right, what other ones we got? 33. Okay. A 2-box problem with one setting on top of the other one. So we got to kind of look at this as a whole, but kind of separate at times as well. So let's read the details here. It says you're lowering 2 boxes, one on top of the other, down a ramp by pulling a rope parallel to the surface of the ramp. Both boxes move together at a constant speed of 15 centimeters per second. The coefficient of kinetic friction between the ramp and the lower box right here is 0.44 because that's sliding. But this one is not sliding on top of the other box, right? Which gives us a coefficient of static friction between the 2 boxes right there is 0.8. What force do you need to exert to accomplish this? What are the magnitude and direction of the frictional force on the upper box? Well, let's first worry about the first question, okay? So, a couple things before we even get into answering that. Since this box is on top of this box, the floor basically thinks, if it could think, that it might as well just be one box, right? All right. So the floor feels like that's a total mass of 32 plus 48, right? So its total weight then is taking that total mass and getting 784. And that also will lead us to the fact that at some point, we'll probably need to know the normal force. And on an incline, the normal force of the incline pushing back is the y, or perpendicular component of the weight, right? So we have the weight, so when necessary, we could find that. But they also threw in a few things along the way that we need, and we have to use basic math or trig to figure out. It didn't give me the angle, right? But it gave me the fact that, they gave me the dimensions of like the ramp, right? Down here is 4.75. The vertical height is 2.5. We treat that like a right angle, and we could just use tangent to find the angle. We'll call alpha here, okay? That makes sense? If we prefer tangent, because this is the opposite over the adjacent, solve it for the angle. As long as we're in degree mode on our calculators, we get just shy of 28 degrees, right? You with me so far? All right. So the next thing... what we're trying to find is what force you need, that person in the picture that's holding on this way. So the applied force is up the ramp. And you don't have to do it this way, but as far as direction goes, especially when friction's involved on an incline, it usually makes the most sense to call the positive direction the way the system's moving. Okay? It's moving down, right? Even though he's just applying a force so it doesn't just completely slide, right? He's like lowering it down at a constant velocity. So I call positive this way, and that makes friction, at least between the box and here, in that direction as well, right? All right, so that's fine as long as you're consistent, okay? I did it with this way being positive, all right? But you should still get out the same like magnitude of an answer if you did everything with the flipped coordinate system. Should still be good. Okay, so anyways, remember for this, since this one's basically attached to the block, we don't got to really worry about that other static frictional force in part A. You know, it's not sliding right now, so all we care about is the incline feels like it's all one block, right? At least for part A. So if that's the case, we have three forces along. Remember, we tilt the axis for an incline, right? So the x-axis is along the incline. We have three forces. What wants to pull the boxes down? The x, or aka parallel force of the weight, right? And we're opposing it, and kinetic friction is opposing it as well, right? So this is where mine says FGX minus frictional kinetic minus applied force. If you flip your coordinate system, that's okay. Yours would then say these two are added together and subtract off this one. Okay, and that's perfectly okay. You could do that as long as you're consistent, okay? Either way, you got to solve it for the applied force, right? Flipping some and just doing some basic algebra and flipping this down, we get this, something that looks like this. All right. Then we remember sub-equations, like remember the x component of weight is equal to the weight times the sine of the angle, right? And friction is equal to mu times the normal force, but in a situation like this, normal force equals the y component of the weight, right? Because all pushes and pulls are horizontal and doesn't affect that, so I could sub all that in. So I noted that here. So once we sub all that in, we find, and by the way, I don't know if I mentioned this or not, well, this is all equal to 0. Why? Back up in this step when we built the sum of it. Why is everything on the right equal to 0? All right, constant v. I mean, typically, if it wasn't constant v, we'd have to keep ma there, right? But since constant v, a is 0, therefore the whole right side of Newton's second law is 0. Then when we plug in all those numbers after all that rearranging, we get just shy of 58 newtons. Does that part make sense? Okay. So the other part is now where we got to focus between the two boxes. Okay? Remember, the reason why this box isn't sliding on the other box is the fact that there's static friction there, right? Now, for the direction of that, we've got to think which way it wants to slide. So I drew a free body diagram on here. Itself has a weight, an x component of the weight that's just based on its weight alone, right? Because it's on top of the box. The box underneath it doesn't affect that, right? That makes sense? Okay. And static friction is pointing up the incline, because this thing would like to slide this way, right? If it could, if there wasn't enough static friction, it would slide off that way. And if that's the way it wants to slide off, friction opposes that, so it has to go that way, up the incline. So that's why I'm pointing here. All right. So what were we asked to find on this one? That's the magnitude and direction of the frictional force on the upper box. And I have a note, there was a given that wasn't even necessary, but it could have maybe tricked you. We'll tell you why in a second. Anyways, this box is also not sliding, so that means the sum of all forces equals 0, right? It's, when we got to be careful how we interpret that. It's sliding relative to the incline plane, but not relative to what we're looking at right now, relative to the box it's attached to, right? It's at rest there. That's why it's 0. And those are the only two horizontal forces. So therefore, flip one to the other side. The static frictional force must balance out and equal with the parallel or x component of its own weight. Just the 32 times 9.8 times the sine of the angle alpha, and we get 146 newtons. Right? And we already pointed out in our diagram that it points up the incline. But the number they gave us that we really didn't need was 0.8. And here's where we got to be careful. They probably gave us this to trick you. Because we could find the max static friction with that, right? We could use that FF, the inequality one. We could use FF static equals mu static, 0.8, times the normal force. But we got to be careful, because that's where most students make a mistake on this one or one like it. If this said it was just about to slide, then we could do that, right? But we have nothing indicating that that's the case. So that would find the max, but that it wanted to find what it really is in this situation. But just for comparison reasons, I got out 146 here, doing it through Newton's second law, right? Had I done the incorrect thing, and let me find the normal force here. The normal force, well, let me say, just for comparison reasons, I'm going to do this. Normal force is the weight, 32 times 9.8, times the cosine of the angle of 27.8 degrees. And that times 0.8. Okay, so if I made the mistake of finding the max when we weren't out of the place that it was just about to slide, I would get almost 222 newtons. All right, but the reason I did that was to compare. Since we don't know we're at the max, it makes sense that this is under that. Remember, static will only be what it has to be, right? And again, so we had to do it this way, using Newton's second law to figure out in reality actually what's occurring, because we weren't told it's just about to slide. And we were told it was just about to slide. We could use the static friction inequality and make it an equality, since would be at the breaking point, but we have no idea that that's the case, and it clearly came out less than that, so it definitely wasn't the case. Any questions on that one? Okay, if we're good on that one, other ones you got? 34. 34, okay. Looks like we got an Atwood system, right? Just with the pulley and whatnot. Some of them became really ugly Atwood systems later in the stuff, but don't get intimidated by them. It might be a lot of work, but just always remember to do a separate free body diagram on each one. And that the tension connecting any and all blocks in an Atwood system is going to be equal, since the pulleys are going to be like frictionless, massless pulley, and the acceleration of everything, since it's all hooked together, has to be equal as well. So let's see the specifics on this one. Consider the system in figure below. Block A weighs 45 newtons. Block B weighs 25 newtons. And it does descend at a constant speed. Calculate the coefficient of kinetic friction between block A and the tabletop. And then we'll figure out part B. So we want the mu K between these two. All right, let's start setting it up. It is at constant speed, so some of all forces on all axes are going to be 0. If we take object A, the normal force balances out with the weight. Okay, right? Because those are only two forces on the y-axis. So those two have to be balancing out. That's why it doesn't fall through the thing. On the x-axis, we have tension minus kinetic friction, right? And if those are only two forces there, and it is going at constant, so that's where we throw the 0 in, right? So therefore, whatever tension is, it has to balance and be equal to the kinetic friction, right? Now, our only knowns are the weights, right? So this is an important thing, but we'll have to basically sub it together with something else, because we still don't have enough to solve for the kinetic friction yet. So let's go over to this guy. This one only has y-axis forces, right? And it's the tension up and the weight down. But don't forget what we do on an Atwood machine. The pulley redirects direction, right? So if we said that this box to the right is positive, which was what's typical, right? Positive wraps around the pulley and has to continue downward, right? So when we set this one up to be consistent with direction in an Atwood machine, we always want to do that. It's going to be this one minus the tension. All right, the weight of block B minus the tension equals 0. Therefore, tension also equals the weight of block B. And we have the mass of block B, so we can find the weight of it, right? So I have tension equals this, and tension equals that. So therefore, I could sub. Then this must equal that, right? You with me? Okay, so when I do that and then I plug in the friction equation. UK that's what we want to solve for, right? Times the normal force that was on block A, right? Is where the friction came in. So that normal force we already said equals the weight of A, so we'll sub in 45 in a little bit. And that equals, by this equation and subbing, 25, right? You with me? Alright, so now since that normal force on block A is 45, we divide 45 over, plug in 25 for that, and get our mu, which typically should be between 0 and 1, right? 0.56. No units because it's mu. Make sense? Right. Most Atwood systems are given as problems because they usually have the need to solve a system. Like get something like tension equals this, tension equals that, sub them together. Or sometimes it could be acceleration equals this, acceleration equals that, sub them together. Okay? Knowing that they're the same for all objects in an Atwood system, that's what makes a subbing possible. Alright, part B. A cat, also weight 45 newtons, falls asleep on the top block A. If block B is now set into downward motion, what's its acceleration? So it's not going to be moving constant anymore because everything was just balanced right to move constant. We're going to slap more mass on top of this one, right? However, and this is the first point I put on this, that won't change the value of mu we found. Why? Because we got to remember the concept of mu. Mu is the texture, roughness, or smoothness between the two surfaces, right? If the cat jumps on top of this block, that doesn't change the two surfaces in contact, does it? This bottom of this block is still sliding on the surface the same. So that means we're allowed to use 0.56 in this. So we had to get part A right to get part B right. All right? And that also changes another thing. Now this block to the table feels like it weighs more, right? Yes. So instead of the normal force equaling balancing out and equal the weight of object A, we have to add the cats there, right? So that's what I do in a step right here. The normal force now equals a total of the block and the cat, 90 newtons. You good with that? And then on the x-axis, we still have tension minus FFK. But now we can't equal to 0 because we have a clear acceleration now, right? And this is a total mass, though. Remember, that block plus the cat. That's what that subscript A plus C is there for. You good? All right, so right there, I have too many unknowns alone to solve, so I go on to the next thing. The same hanging block is over there, so nothing changes with that, right? We still have that same formula, other than the fact it's not equal to 0, right? So this is for the other object, Newton's second law. This is just mass of object B, because it's set up just for that object, right? And again, we have a tension substitution. If tension equals all this and tension equals all that, it does get uglier mathematically when it's not at equilibrium because just more terms are around, right? But this is still the same idea. So we sub all this equal to all that. And now we solve for acceleration. All right? We get all the A's on one side. So I rearrange it just like you would do in like Algebra 1 if you had X here, X there, get them all on one side, right? So I get all the A's on one side, then I could factor it out of this term, leaving me the leftovers of the combined masses here, all of them. So I could divide that term in parentheses over for the proper algebra, and now I could plug everything in. And at the same time, for FFK, I'm plugging in UK times the normal force, which we found early on, which was the combined weight of the cat and the block A. So plug in all those numbers, and acceleration is negative 2.15 meters per second squared. It should make sense it comes out negative. That represents, since the way it was moving is positive, remember, it was in motion and the cat jumped on it, right? And it was moving at constant velocity, so a cat on it would slow it down, right? Which makes sense why the A came out negative. It's moving in the positive with a negative acceleration. That at least all links up that it should be a negative number. Does that all make sense? Okay. Great problem with a smiley face. Anything else? Okay, I'm gonna go into a few that's some email. I'm just gonna check my email once again to see if any. Okay, nobody else gave me any. So since this morning, so we had 10, 65, 92, and 97. So let's go back to number 10. Okay, number 10 was an equilibrium problem, but it had like several things hanging from like knots and several forces. Okay, so they give us a diagram that looks something like this. I also broke some things up into components on mine, but it says in the figure below, the weight W is 60 newtons. That's the object hanging off the bottom. What is the tension in the diagonal string for part A? Okay, so we want this overall tension. It's at an angle though, right? Anytime we have any forces at angles, we break them into components. Now, I showed it both ways only for the purpose of really this problem. When we find the x component of tension, it acts this way on that first knot. But that same x component goes across the board. It also acts down here on this knot, that same tension, okay? Opposing this one. Same with and then the y tension is what supports everything up. As far as part A goes, and finding that tension, we could, for this part, kind of pretend for right now that this knot is the ceiling. The whole system's not moving, right? Yeah. All right, so because of that, we just know that the only two vertical forces that exist here, all right, if we pretend it's like linked up there at like a ceiling at that point, we just have the y component of tension up, and it has to support the weight, right? So that's what I have here. Ty minus weight equals 0 because the whole system's in equilibrium. All right, and when we break up, we know the angles here, the way they gave us. This angle is 45. Therefore, this one's 45, 45, 45, right? Because of the nature of 45, 45, 90 triangles. And that means we could use the sine of 45 for Ty, given in that place. And actually, since it is 45, sine or cosine are the same. But that's unique to this problem. It doesn't have to be that way. So when we plug in that for the y component of the tension, and we know it must balance and be equal with the weight because of what we set up here, we could solve by dividing over sine of 45 to get the tension. Overall tension is what they asked for, of 84.9 newtons. Okay? Then we now want to know what this F1 and F2 are. These pull horizontally. All right, so let's just look at the top knot to begin with. On the top knot itself, I'm just going to perform Newton's second law and imagine just a free body diagram on that. We have a left force and a right force. They have to be balanced, right? If this whole system's in equilibrium, this x component of the tension that we just found has to be pulling with the same amount as F1, or in other words, Tx minus F1 equals 0. Otherwise, if one of those was pulling harder, the system would be moving. So since they're equal, F1 must equal that component. That component is T times the cosine of 40. If we use the broken up angles here, again, they're 45 though. Plug in the numbers and we get 84.9, the overall tension which we solved for, times the cosine of 45. That's got to be 60 newtons up there. In a similar way, F2 also has to balance with that x component down here because that's the only two forces on it. So if we do it the same way, it's no surprise that it also comes out 60 newtons. Okay? So it balances both of those and the whole system stays in equilibrium. Alright, since the bell's going to ring in a few minutes, I'm going to pause it, and when we pick up next period, I'll answer the rest of the questions. For those of you at home, I will post 2 videos, a second part to this one.